such that, see here, so x1 to xk, any arrangement from this n strings, x1 to xn, on the left hand side, and the right hand side, any arrangement from the list n, y1 to yn. Take k strings and arrange. So that these two strings, the arrangement should be in such a way that LHS is equal to RHS. The string should be equal. Are you understanding? So we'll see, we will understand more when we see an example. So if you are able to get LHS equal to RHS, then we see that it's a post correspondence. Okay. So our question is, can I design a generalized algorithm given two list of strings? So the output should be arrangement. Okay. So if my output is say 1, 2, 3, 1, 2, 3, that means x1, x2, x3 should be equal to y1, y2, y3. The strings x1, x2, x3 concatenated together and written together should be equal to y1, y2, y3 if this arrangement is like this. Remember, the indices should be in the same order in LHS and RHS. If it's 1, 2, 3 this side, it should be 1, 2, 3 this side also. You cannot mix the order. Order is also important. Okay, so it should be in the same order on both the sides. Okay, so if I am able to get a LHS equal to RHS by making any arrangement, but it need not be in 1, 2, 3 alone. If I can make 3, 3, 1 also, the strings could be repeated also. But if it is 3, 3, 1 in the LHS, right side also, y also should be 3, 3, 1. So if it is x3, x3, x1, right hand side, it should be y3, y3, y1. So if this arrangement gets me an LHS equal to RHS, then I mean that, okay, this satisfies the post correspondence. I'm able to create a post correspondence arrangement out of these two lists. So that is the conclusion. So what is the problem is, so given m and n, is there a generic algorithm? Can I write a generic algorithm for any list of m and n from any alphabet, over any alphabet, that gives me a single arrangement? Okay, that gives me a single arrangement that satisfies this post correspondence property. Okay, so the concept is like, there is no single, you cannot write, see, when the strings, number of strings is huge, and the rearrangement also has a lot of possibilities. As you can see, repetitions are allowed, and the order also, it can be in any order. But LHS and RHS, the indices order should be the same. That is the only requirement. But any number of times you can repeat, you can ignore some strings, you can arrange in any order, and given all these flexibility, so writing a generalized algorithm, okay, only in this way I'll get this output string. So writing this generalized algorithm that holds good for any list with any length over any alphabet is not possible. So this problem again becomes undecidable. We will have a dedicated proof of how we are saying that this problem is undecidable. As we saw, reduction, there are three principles to prove that a problem is undecidable. Okay, one is diagonalization and one is reduction, and the third thing is Rice theorem. Rice theorem is also helped to prove that a problem is undecidable. Okay, there are three ways in which you can prove a problem to be undecidable. One is diagonalization, the second principle is reduction, and the third principle is Rice theorem. Okay, so we are not going to see diagonalization. We'll see reduction, because reduction is a very, very powerful technique, and you can see reduction in almost all research papers that handle NP-hard or NP-complete problems. They would have given a section that proves that their problem is NP-hard and NP-complete. And the proof is either if it is decidability or if it is complexity, they would have reduced that proof only from a known problem. So it's a reduction process. They would have reduced their problem from a known standard problem, which is known to be undecidable or which is known to be NP-hard or NP-complete, and they will prove that their own problem is NP-hard or NP-complete, or their problem is undecidable. Okay, so a reduction is a very powerful technique. So we'll see two examples for reduction today. Even if you're not understanding at the first time or the first time of while I'm explaining, please have patience and watch the recording again. You'll definitely understand. And this reduction principle is definitely going to help you in case you're going to go for higher studies or research, because you cannot write a paper that handles a NP-complete or NP-hard problem without reducing it from a known problem. Okay, we cannot just go and say that my problem is NP-hard. So you have to give a mathematical proof. You have to reduce your problem from any one of the known standard problems. Okay, so today we are going to see the reduction. Okay, so three principles: diagonalization, reduction, and Rice theorem. Why are these three used? Using these three, you can decide if a problem is undecidable or not. Okay, so we are going to see the reduction concept today. So first we'll see, we are now taking an undecidable decision problem called post correspondence problem. So like we have seen the general definition, I think it will be, we can understand more when we see examples. See, these are over an alphabet A and B. So I have an alphabet A and B. So I have M is a list of, so the length N is equal to 3. So I have two lists M and N of length 3. Okay. So M has 3 strings and N has 3 strings, and these 3 strings are built over this alphabet. Okay. Now, does it have a post correspondence solution? So questions like this only will be asked. Okay. Does this strings have a post correspondence solution? So what should we do? We know this is string 1, string 2, string 3, 1, 2, 3, and similarly this is y1, y2, y3. Okay, so you should arrange in some order so that you get two strings equivalent LHS and RHS. Remember, LHS, if it has some order 3, 3, 2, 1, RHS 3, 3, 2, 1 means it is x3, x2, x2 again, and x1. Then again in the RHS also you should arrange in the same order. Okay, so by arranging this order, arranging M and N in some order, if you're able to get same strings as output, then this list these two lists have a post correspondence solution. Okay, and one more thing is like you have to remember, you can it allows repetition also. Say you can place any number of times a string any number of times at any positions also. That also you have to remember. Okay, now we'll check if this has a post correspondence solution. Okay, so now I am trying an order of 2, 1, 3. So I'm writing x2, x1, x3. Let us take x2 is AA, again x1 is ABB, and x3 is 3A's together. Okay, so this is my LHS with x. Okay, let me take y again. So I'll try y2. Y2 is what? So this is y also. The second one is y. Okay, so y2 is this one. So I write, so the first one is x2, x1, x3. So AA was x2, x1 was ABB, this was x3. Okay, x2, 1, 3. Right, this is x1, I'm sorry, x2, x1, x3. Similarly, I'm going to write y2, y1, and y3. So what is y2? AAA is y2. Okay, and y1 is BBA is y1, and what is y3? 2AA are y3. So if I follow the same order of 2, 1, 3 in the LHS and RHS, I'm able to get the same string. Okay, I'm able to get the same string. Now you can also prove that. How do I prove that? Like I cannot write a generalized algorithm that gives me this ordering. Given list two list M and N, I cannot write a generalized algorithm that gives me all possible post correspondence solutions. Now please understand that need not be only one string as output. I can write multiple strings like this. Is it possible to write an algorithm that gives me all post correspondence solutions given two lists of strings over an alphabet? No. No generalized algorithm can give you all possible set of strings because there are numerous arrangements possible. Okay, so if you are asked, you'll have to write this order, and if possible, write 2 orders. Okay, in the exam, please write 2 orders and prove that the multiple orderings are possible. So there is no possibility to write a generalized algorithm that gives me all post correspondence solutions for this given string. Okay, so the things that we have to remember is the indices order should be same in LHS and RHS. If it is 2, 1, 3 on LHS, it should be 2, 1, 3 for RHS. Now, where did I get x1, x2, x3 and all? That is given as input for me. So M, the 3 strings are x1, x2, x3, and this is x1, x2, and x3. This is y1, y2, and y3. So these are given to me. So my work is I have to make an arrangement. Okay, in doing that arrangement, please preserve the order of x2, x1, x3 means here also it should be y2, y1, and y3. Okay, so multiple orderings are possible. Okay, and so I cannot write a single generalized algorithm that gives me all this possible orderings. Okay, so I consider this problem as undecidable problem. We later prove that this is undecidable problem. And one more thing, to prevent this, to preserve this ordering at both the sides, we construct the representation. They'll also give it as dominoes. Dominoes as in they'll create something like this: A B B Y B B A. Can you see? This is x1 by y1. This is a domino. The second domino is AA by AAA. This is easier because you have to preserve the indices at both the ends. So the representing these strings as dominoes will help the rearrangement faster. So in our computer implementation, generally we do implement it like this. Okay. So more natural representation is we represent it as dominoes. So each domino is x1 by y1, xi by yi, the same index, so that we don't confuse the index hereafter. Okay, so given these three dominoes, my post correspondence solution should arrange its dominoes in any order such that I'll get the same string in the numerator and denominator. So we got a 2, 1, and 3. So this is 2, 1, and 3. So when I arrange it like 2, 1, and 3, the domino AA and AAA, then ABB by BBA, and then a 3 AAA by AA, I can get the same string in the numerator and I get the same string in the denominator. If you concatenate it together, I get the same string in the numerator and the same string in the denominator as well. Okay, so this problem, this given list has a post correspondence solution. Okay, I've done the same thing here. I've given you an idea of representing the strings, list of strings as dominoes. So having this as dominoes will help us in solving the problem. Then working out will be easier and arranging also will be easier. Rather than having it as individual string, we can club together according to the index positions. So x1 and y1 combined together will be the first domino, then the second domino, third domino, and so on. So that the rearrangement is easier. Okay, so this is the concept of post correspondence solutions. The next example again. So this is x1, x2, x3, y1, y2, y3. Now again, a post correspondence solution. Okay, so again 2, 1, 1, 3 is another solution. As I told you, see 2, 3, 1 also gives me same strings on LHS and RHS. Again 2, 1, 1, 3, this arrangement also gives the same solution on LHS and RHS. Okay, so this is how you should write in your exam. So you can say, you can find just by trial and error, you just find the arrangement of dominoes. We'll see a problem that will help us, like how we can find such an arrangement. We'll see a shortcut, not a generalized algorithm, just a very shortcut or a heuristic, we can say, that helps us to make it converge faster, may find the arrangement faster. Convergences, I'll find an arrangement faster. Okay, so as you can see here, I found multiple assignments, right? Multiple arrangements. I can find many number of arrangements like this. That's why I say there is no generic algorithm that gives me all possible arrangements. Okay, so this is a post correspondence solution. So you'll be given two lists in your question. You might be given two lists and you might be asked, like, does this have a post correspondence solution? Please write to at least two possible arrangements. Have it as dominoes. Okay, so have it as dominoes. So for example, if you take the second domino, you'll write it like this: 0, 0, 1, 1 by 0, 0. The first domino will be 1, 1, 0 by 1, 1, 0, 1, 1, 0. This is the first domino. And the third domino is 0, 1, 1, 0 by 1, 1, 0. Okay, so you'll have three dominoes. Just rearrange it accordingly and find the solution. Okay, so give at least multiple solutions. Okay, and there's one more version called modified post correspondence problem. This modified post correspondence problem will help us to what it will do is it will help us to prove that this is undecidable. In modified post correspondence problem, it's just a very simple thing is like, keep the first string in the list as constant. Don't move the first one. Okay, so always it is like LHS and RHS will have the first string as starting. This is fixed. Okay, the first pair should be fixed at LHS and RHS. Please fix it. So instead of X and Y, they've given W and X here. There's just a difference. So the concept is have X1 and Y1 or W1 and X1, the first pair in both the sides. Okay, the first string in both the sides. That pair, you have it as constant. After that, you can shuffle, you can rearrange, you can even repeat one somewhere in between. Not a problem. But the first one should be the first string. So when we have that, it is easier for having a lot of derivation. So this is called as modified post correspondence problems. Generally, every post correspondence problem is a modified post correspondence problem. The reverse is not true. Okay, the reverse is not true. Every post correspondence problem, one of the arrangements you can have, like the first one is always a first string. So every PCP is a modified PCP, but converse is not, reverse is not true. Okay, and the next thing is, like, I think we can. This is the modified post correspondence problem. Now it says, like, you can see in both the sides, you can see the first string is retained as such, right? So the first string is W1 and this is X1. You can see 1010 is retained. After that, you can do any arrangement. 2 or 3 or 1 could occur again. So in that case, if you're having the first string is constant and then you do any shuffling, this is immaterial. Any ordering at any number of times it can occur. Anything is possible. Just have the first string as constant in LHS and RHS. So by having that, if you're able to prove the post correspondence property, then it is called as modified post correspondence. Okay. The reason for having this is only it is easier to prove that your post correspondence problem is undecidable. Okay? That's the only reason that we are having that. So before